Okay, how's that? Is that okay? Great. Well, thank you very much for that great introduction. When people say those sort of things, I'm thinking to myself, did I really do those things? And I think I did most of them, so it's okay. So thank you very much for a very kind introduction. Great to see you all coming out on a pretty wet and horrible evening in the dog days of January. As Dish said, and as it shows up there, let me see if I can. Yeah, that's me, and I am at Oxford University and BCAST at Brunel University, and I'm also a co-director of the Interdisciplinary Centre for Circular Materials and Metals, and we've just set up a UN centre in that activity too. And I'm going to talk about multi-component high-entropy Cantor alloys. I have to always say they're named after me, and I seriously, folks, I didn't name them after me. Someone else named them after me, and it's very nice they did so, but it's mildly embarrassing, perhaps. But anyway, there it is. And before I start, my book, I stopped running universities. I decided to give it a break. I've been running universities, indulging in that for about 20 years, and was getting a little bit tired of the work. It was getting a touch samey, although there's always new challenges. But I gave it up partly because this field of multi-component high-entropy alloys was going like a bomb. It still is going like a bomb, and I'll say a few words about that in a minute. But one of the reasons so I gave it up because I wanted to write a book on the field, because I had invented the field, and my book actually came out at the end of November, beginning of December. So for those of you who are interested, do have a look and see if you want to find out more about the field. There it is. I've got 4 take-home messages I want you to have from this lecture. Human history is the history of new materials. In the process of writing this book, I realized how important materials are. I mean, I've been a material scientist all my life, and it never occurred to me just actually how important they really are. So human history is the history of the development of new materials. All major advances have happened with the development of new materials. Sometimes they're rather quite complicated and difficult ones, but it's surprising how true that is, and I hope to persuade you of it. Secondly, all materials are alloys. What is an alloy? It's really, what it means is all materials are made up of other materials mixed up. Starting materials. We always mix more than one starting material to make any real material. Or we unavoidably have more than one material mixed in. They're technically called components. So we mix up components or starting materials to make the actual materials that we use. And you'll hear, I hope to persuade you that that's the case. You'll see that it is the case. Thirdly, there are gazillions of materials. Gazillions, not a very technical term, and I will give you a definition of what I mean by gazillions when I come to the point about how many materials actually are there. But anyway, there's a hell of a lot of them. I'll hope to persuade you of that. And then multi-component alloys are going to be important to us for our future well-being, just because we want to continue to develop, and so we need to develop new materials. And what this whole field has done is open up a vast new arena of new materials which we can make. So suddenly, the range of potential materials has become much greater than we really had understood. We kind of knew it, but we hadn't bothered to investigate. So those are the 4 things I want you to go away with. And so the first section of my talk, therefore, is a quick run through the history of the world as a history of the development of materials. So I'm going to start, though, I'm just going to think about humans, really. Humans emerged about 3 million years ago. It was the beginning of the Ice Age 3 million years ago, and that's why humans emerged. It got colder. Apes began to evolve and develop slightly bigger brains so that they could make tools to go and chop down trees and hunt for animals more effectively. So it's fairly obvious why that happened. And the material that led to that, of course, was flints. So it's a found material. Well, it was manufactured. Flints are sharpened by striking them to make them into tools to give them a point. And the fact they're an alloy So they're fairly pure. Flint is fairly pure silicon oxide. It's got a rather complicated internal structure. It's not a single crystal or anything, but it's got a fairly complicated structure. But it's got little bits of impurities in it, like calcium oxide or iron oxide or something, and it's that allows you to fracture it when you strike it to make it into a tool. So the fact it's an alloy is very important. So I'm going to jump forward almost 3 million years, because you may not know, but the last ice age, which began 3 million years ago, lasted almost 3 million years. It finished just 99.5% of the last 3 million years, we were in the ice age. And humans were wandering around with these flint tools in small groups, just like to try and get their food. About 12,000 years ago, 10,000 BC, is when we had something called the agricultural revolution, which is sometimes called the biggest change in human existence that ever occurred. And it's when, it's because, it was driven by the fact the ice age was finishing, it was getting warmer, it became possible for humans to settle down in farming communities, and that's when they domesticated animals and domesticated plants, and they could farm them. So prior to that, they had to wander around, be hunter-gatherers, work a bit, live a bit like apes mostly do now. And it wasn't until the agricultural revolution, about 10,000 BC, that they began to settle down in farming communities. Now, it's often said that the domestication of plants and animals was the key driver. But the truth is that if they didn't have a material called fire clay, it wouldn't have happened. So clay is another, fire clay is what you use to make bricks and pots, things like that. So you mix up aluminium oxide and silicon oxide and maybe some bits of other things in the right proportions with water, and you fire it, and you can make it into shaped objects. And now there's not much point having a farming community, settling down in a farming community if you haven't got good houses. You can make houses out of stones, but they're much better if you can shape the stones more effectively and make bricks. Even more important, there is no point domesticating animals or plants if you can't store the food from them. It just goes off. You might as well wander around and just gather it as a hunter-gatherers. So the material was absolutely essential to the agricultural revolution. Well, about 6,000 years later, about 4,000 BC, I want to say, it's not true, I want to say that the Stone Age people discovered metals, but they didn't. They already knew about metals. Metals are made, all the early metals were made by smelting. Smelting is when if you have a fire. So Stone Age people would have fires just to make themselves warm, or they would have fires to fire the fire clay to heat up the things to make pots and so on. And if you have a fire on top of an ore, an oxide ore, most ores, most rocks are oxides, then the carbon in the wood for the fire reacts with the oxygen and goes off as carbon dioxide. That's a big problem these days, but that's what happens, and it happens small scale in those days. And you leave the cation, the metal, as a pure metal. It gets smelted. So Stone Age people, I like to think, must have been amazed when they occasionally saw bright, shiny metals dripping out at the bottom of a fire. So they knew about them, but they were pretty useless. The early metals were copper, silver, tin, lead. They were low melting point metals, and pure metals are very soft, and they were pretty pure. So they were used pretty much for decorative purposes only, until someone discovered, and we don't know how they discovered it, because it's an amazing discovery, that if you add a little bit of tin to copper, you can make bronze, and that's why the Bronze Age began. And if you add a bit of tin, it makes it hard as well, so you can shape it. The characteristic feature of metals is you can shape them because they're soft, but you can also make it hard enough to be useful and make really good tools, much better tools than the stone tools that were being made out of flint. Now, the reason it was difficult to discover this is that copper and tin ores are not usually found in the same place. So, in fact, the growth of the Bronze Age, which gradually built up, led to a massive change in society. Instead of farming communities, we started to have what we call Bronze Age civilizations. We actually started to have cities. We started to have trade. We started to have industry, because you had to have mining of copper, mining of tin ores. You had to have smelting of them. You had to have them transported around. People had to own this sort of thing to make it happen. And the people who owned that became the kings and the emperors, and you develop cities and trade. And all of that begins because of the discovery of the use of metals in the Bronze Age. And all these great civilizations, the earliest Chinese civilizations that are known were Bronze Age civilizations. The Mayan civilization in the Americas, in Mexico, was a Bronze Age civilization. The earliest known ones in this country were the most famous, almost certainly, is the pharaohs in Egypt, who lasted for a long time. They were Bronze Age civilization, and they all collapsed about 1500 BC. So about the Bronze Age period lasts from about 4000 BC through to about 1000 BC. And between 1500 BC and 1000 BC, all those civilizations I mentioned, they all kind of collapsed in a period of about a few hundred, 200-300 years. Now, the Minoan civilization, for instance, is often thought to have collapsed because there was a massive volcano which erupted. There was some bad government amongst the Egyptian governments and so on. But the underlying reason was the economic one associated with the development of the Iron Age. So the Hittites in Turkey are the first people who discovered, in what's modern day Turkey, who discovered iron. And the reason people hadn't discovered iron before is because iron's got a higher melting point, so you needed to have better quality fires. So fire technology improved, and finally people began to be able to make iron ore. And iron's got two major features. One is that it's everywhere. There's not that much copper ores, there's not that much tin ores, but there's iron ores everywhere, so anybody could make it. Now the Hittites kept it to themselves for about a couple of hundred years, but finally it got discovered and others began to make it. So everybody could make their own iron ore, and that's why other new civilizations grew up and ultimately took over from all the Bronze Age civilizations. Iron has another characteristic, which is that it, unlike copper or tin or lead or silver, it absorbs the carbon. So you don't have to do a conscious alloying like you did with bronze to add the tin to the copper to turn it into an alloy, into a mixture, to get the right combination of shapeability and softness alongside the strength you needed. It did that automatically, and it's much stronger and much better material. So the Iron Age the most famous Iron Age civilization, the Qin dynasty in China, which China is named after, was the first Iron Age dynasty in the Far East, and there's a whole series of them. The Celts here in this part of the world were Iron Age, but the most famous one is probably the Roman the Roman Empire. Well, we jump forward to the Industrial Revolution in the 18th and 19th centuries. That was built on the scientific revolution of the late 15th and 16th century and the discovery of science, and we're all scientists here, or I imagine most of us are, so we know about science, and of course it was until the 15th and 16th century, it was widely thought that the way you got knowledge was by thinking hard and coming up with the right answer. And that's why, knowledge came from the Bible or from Aristotle or, great people who had great thoughts. People didn't trust looking at stuff. It wasn't until it was done very carefully that one was able to sort of tease out regularities which allowed one to develop some science. And that was kind of, that's famously Galileo and Copernicus and so on demonstrated that science worked, and the scientific revolution is thought to have begun with them and then ended roughly with, didn't end, but reached its sort of first triumph, full triumph with Newton's Principia and the explaining how the planets worked and forces and all that, which you know about, everyone learns about. In the next couple of hundred years, though, in the 18th and 19th century, those principles began to be applied, and gradually you develop what we would now think of as a modern society via industrialization. So machinery, all engineering, power plants, electricity, transport, building of skyscrapers, you name it. All the things we see now as characteristically part of what it is to live in a developed part of the world. And not all of the world has gone through its industrial revolution, of course, still. But it began very close to where I live at the moment, which is in Hebden Bridge up in the Pennines. So it began up in Mid Lancs and Mid Yorkshire. But it gradually spread out, and it led to a massive growth in wealth and health for people. So the developed world, which we know about now, has fairly comfortable existence. That's what we all do. China has gone through its industrial revolution probably in the last, it went through it, 20, 30 years ago or something, in the end of the 20th century, and India too. And there's still massive parts of the world which haven't gone through it. But it was the second biggest development of human existence, probably. It led to an enormous change. We stopped having people living as starvation farming economies, working like crazy and just about getting by, and we started to have people having disposable income and living what we think of as comfortable lives. But it was based on the development of steel. Now, steel was known about, but it couldn't be made very well until the mid-19th century. Steel is paradoxically a slightly purer form of iron. Iron is iron with cast iron and wrought iron, which is what the Iron Age was built on, is iron with about 1 or 2% of carbon in it, because it naturally absorbs it, and that's very important to given its properties. But you actually get a better, more controllable material if you can take some of the carbon out and get it down to a fraction of a percent. And how to do that controllably was discovered really in the 18th and 19th century, and it's the basis of the whole of the Industrial Revolution. You couldn't have the precision machinery that you need for the whole of the Industrial Revolution without that. And then the third biggest change in human existence is often said to be the information revolution. And of course that depends upon silicon chips, computers, these sort of things, telecommunications, all the modern massive amounts of data manipulation, it's social media, you name it, is all based on the discovery of silicon chips. And silicon chips are made out of silicon, fairly obviously, but they are alloyed, microalloyed, doped with small amounts of phosphorus and aluminium and boron and so on to give them their very, very highly controlled properties. So again, you have an alloy which is controlling the development of humankind. So I'm going to just quickly flip through a couple of, I should put my glasses on, then I can see what I'm looking at. I'm going to quickly flip through just a few slides just to make the point a little bit more. So there's, does it work if I do this? Can you see that? Yeah, that's easier. Then I can look here instead of looking up there and cricking my neck. So there's an old flint chopping tool from a couple of million years BC. There's a bronze dagger. It's got a little bit oxidized from about 1500 BC from the Bronze Age. That's how they would. That's what a kiln would look like. Kilns are perhaps an excessive word, or a. That's actually probably a copper. It says a copper smelting hearth. It's from the Bronze Age. It looks like the sort of fire you'd make outside your tent, if you were going out camping. But the key development, by the way, technologically to make fires better was the discovery of chimneys. You put a chimney on. So this is a Greek vase showing a chimney on top of a fire here, and here's a Greek blacksmith. It's hot, so he's not wearing very much, which looks a bit dangerous. Pulling out an iron bowl and turning it into tools and things like that. And then if you go to the Industrial Revolution, go back. You can control now the steel. If you have, it varies from about 0.1 to 0.8% carbon. At the 0.8 at the top end, you get the harder materials, and you can make wonderful tools like these beautiful Damascus steel knives. And you can get, if you go at the bottom end, you get more shapeability, so you control the carbon to control the balance, and you may get this even more wonderful object. What I would have loved to have had, a golden era two-tone Cadillac. The real era of wonderful cars was in the 1950s, and that's a 1950s car. And then the information revolution. There's a couple of slides just to show what it's like. This is not now the state of the art. This is a 2 meter tall, 200 millimeter diameter, but they're considerably bigger now. Single crystal, parts per billion purity. An amazing object, really, when you think about it. Which then is cut into thin wafers. There's one of them, so there'll be several hundred of those cut from that. And on top of that, you would pattern each of these is a silicon chip. So you get several hundred silicon chips out and several hundred wafers out of this. So you get a lot of silicon chips out of one of these silicon single crystals. And inside that silicon chip, there are up to now something like 80 billion individual transistors, which is an amazing number. This is an electron micrograph of, I'm not going to go through any detail, but that distance there is about 10 atoms. And these different regions have been doped differently, they're alloyed differently, and it's all of that control of all that. Fantastic technology to create that, then to create that with this sort of level. It's just unbelievable, really. And that's what the basis of all of our computer information technology is made through. And it's all based upon the understanding how to alloy silicon. Well, I hope I persuaded you my first two take-home messages. The development of the world has been developed through the development of new materials. Those are the biggest events that have happened since humans emerged. And the materials we use are nearly always alloys. They're mixtures of other materials. Now, all of the materials we've developed until very recently have been developed using what I now call a conventional alloying strategy, where you nearly always take one, occasionally two, major components for the main property and add a small amount of alloying additions, a small amount of something else to tweak up the properties, to either add a secondary property or to tweak up the main property. I'm going to give you two other examples quickly. Aero engines were invented, jet engines were invented by, first thought of and invented by Frank Whittle in the 1930s. And they were kicked out by the RAF, by a very famous metallurgist working in the RAF, who said they'll never fly. And he said there's no material hot enough to cope with the temperature which will be generated by an aero engine. The very same year that Griffith turned down Whittle's proposal, the answer was patented, which was the development of what's called nickel superalloys. It was developed by three people, and it was in the 30s. But it wasn't until the 50s, so because we didn't have the suitable material, that jet engines really began to be developed. So it delayed the development of jet engines that we didn't have a good material. Nickel superalloys are nickel because nickel's got a higher melting point, so that solves the main problem. But then you add a little bit of titanium or aluminium to make it a bit stronger, and you add a little bit of chromium to make it corrosion resistant, and both of those are important. So that's a very typical example. I'm going to give you a completely different sort of example because I've talked a lot about metals. I'm actually a metallurgist originally, although I've worked on a lot of other materials. But I'm going to give you, I've been talking, of course, about semiconductors as well, but a ceramic example, a well-known one, is window glass. So window glass is made out of silicon oxide. If you cool silicon oxide quickly, you don't have to cool it very quickly. If you cool it when it's melted, it goes amorphous. The molecules don't line up in a crystal structure; they go very amorphous, and that allows it to become transparent, which is why you can see through glass. That's quite useful. But to make window glass, you add a little bit of sodium oxide to lower the melting point, because it makes it easier to handle the manufacture. And you add a little bit of calcium oxide, a few percent of these things, of lime, calcium oxide, to stop it devitrifying when you use it. So window glass is, those are just two completely different examples where you've got a main component and two or three addition elements. So that's what conventional alloying strategy is. So we come to multi-component materials. And in the late 70s and early 80s, I began to say to people, why do we never add large number of components in equal or near equal proportions, as it says up there. I started going around. I was at Sussex University as a postdoc at the time, and everyone said, because it's bonkers, it doesn't work, it's crazy, don't be silly, go and do something more useful, Brian. Don't be daft, it doesn't work. It was widely known that adding too many alloying elements in too high a proportion didn't work. I'll say a little bit more about that in a minute, in a later slide. I'm just going to show a little bit more what I mean, though. If you take a three-component system like the nickel superalloy, or the window glass, we look at the composition on what's called a ternary phase diagram. Technical term, you don't need to know what that means, but we put nickel at the corner of a triangle, aluminium up there, which is we're going to add some aluminium to strengthen it, and we're going to put some chromium. We put pure chromium at this corner, and any point in that region is now a different composition of nickel, aluminium, and chromium.
I can't see what your point is.
Oh, you can't? I thought you could see it. I'm sorry. In that case, let me show you then. So we put nickel there, chromium there, and aluminium there, and every point in this triangle is now a different composition of nickel, aluminium, and chromium. If we have a four-component system, then we can do it with more difficulty, because it's a three-dimensional object now in a quaternary phase diagram, but you get the idea. So what I'm really saying is that most of our materials, not all of our materials that we've used up until very recently, are down in these corners here. The nickel with a bit of aluminium and a bit of chromium. So it's all up in the nickel corner. If you take silicon oxide with some calcium oxide and sodium oxide for window glass is in this corner here. Occasionally we're on the edge here. But the central region of most ternary systems, most three-component systems, most materials made out of three starting materials, we don't know much about. We've never made them. Even just three components. I was thinking of more than that. If you go to four components, forget it. Nobody's hardly ever made any of them, because everyone knew it didn't work. I'll say why they thought it didn't work in a second and why they were wrong, but as it turns out. But and if you go to 5, 6, 7, component systems, no one had ever made any of those, and everyone just knew it was one of those taboo, almost a taboo. If you add too much alloying elements, you get a material that just doesn't work. Well, I was a bit cussed, maybe, I don't know, and what happened was I finally persuaded I couldn't get anyone to study this. All my colleagues, my academic colleagues, said to me, they patted me on the head, Brian, there, you go and lie down and you wear off after a while. My research funders were not going to give me any money to work on some crazy idea. And even more importantly, research students wanted to work on something. They didn't want to work on some topic which was, because when they wanted to get a job at the end. They had the best reason. They wanted to be able to work on a topic that people had heard of. But I finally persuaded a young man called Alan Vincent, who was an undergraduate student, to do an undergraduate project on this. And he was a more adventurous student. I didn't, so we made up several alloys, only about 3 or 4 alloys. But one of them, we didn't know what to, we had no guidelines about what to make. So we did something which I thought of as parachuting into the middle of an unknown continent. We just jumped in and made 2 or 3 or 4. Basically, I went to the materials cabinet and I pulled out all the materials we had, and I said, well, let's just mix them all up, melt them all up. And so one of the materials was, for many years, it's not any longer, the world record for the most components in an alloy ever made. It was all the things that we thought we could conceivably just about manage to melt together. We made 5%, we weighed out 5% of each of those and mixed them up together. We made another one with 10 or 12 components, I forget exactly how many, where we took out some of the things which are more likely to vaporize or be difficult to handle. And we made 3 anyway. I don't. But this is the one that had the most components in it. and makes the point best. And the first thing we discovered was everybody was dead right, because this material, this is an optical micrograph of what it's like. It doesn't give the dimensions. This distance that's about 100 microns. So this is typically what you would see in a microscope for a material, an optical microscope. Nothing too fancy. And it's a mess. There's loads of different compounds in here. The X-ray trace when we took from it had loads and loads of X-ray diffraction lines, because there were lots of different compounds, and therefore you're getting all sorts of diffraction from each of them. And that is why and it cracked up. It sort of partly went into dust when we made it. It wasn't a usable material. But the second thing we discovered within about a week was that everyone was wrong, because this black region, or some part of this black, some of these regions here, turned out to be what's now called the first Cantor alloy. This is the Cantor alloy. The Cantor alloy is a equiatomic mixture of chromium, manganese, iron, cobalt, and nickel. We discovered in the middle of that mess of lots of compounds a region which had 5 components in it: chromium, manganese, iron, cobalt, and nickel, with a single simple crystal structure, face-centered cubic. This is a face-centered cubic crystal structure. Fairly obviously, it consists of a cube with atoms at the corner and atoms at every face. That's what makes a face-centered cubic crystal structure. Most metals have that structure: aluminium, silver, gold, lead. Lots of metals have this structure, and it's this structure which is particularly shapeable and formable. The reason metals are soft and formable is because this structure is very able to do that. We don't need to worry about the details of why, but anyway, I might actually say a word about that later. Not much about it, but anyway. It's this structure which is characteristic of metals. Now what happens when you take copper and you add tin to it is this. Initially, of course, in a piece of copper, the cube of copper atoms like this is stacked up in order, to make a large piece of copper. If you have pure copper, that's what it's like. If you add a little bit of tin to it, for the first about 0.01% of addition of tin, 1 or 2 of the tin atoms replace the copper to form what's called a solid solution. But once you get much into adding much tin, you start to form a compound, a copper-tin compound. It's actually Cu6SN5. And that's what gives the material its strength, these little hard. But if you add too much, it becomes a mess. So much compounds that the thing sort of becomes. If you have a high tin bronze, it's nowhere near as useful as the standard bronze has about 10% of tin in copper. Same thing happens. Iron, we're not going into the details of it, is not actually face-centered cubic, but the same thing basically happens when you add carbon. At first, the carbon goes into a solid solution, but if you add too much, you form a compound, iron, called cementite, Fe3C. That doesn't really, you don't need to know about that, but that's what happens. So the typical thing that happens when you start alloying is you can get a little bit of replacement on the crystal structure, but once you start adding any amount of alloying element, or certainly if you add lots of different ones, you start to form compounds. Because when you mix different stuff up together, we know that they form compounds. That's what chemistry is all about. Now, this material, which we discovered in the middle of our 20-component material, consists of a face-centered cubic structure with a random arrangement of 20% of chromium, manganese, iron, cobalt, and nickel atoms randomly distributed onto this. Nobody could have predicted that. Nobody did predict it. It was entirely a surprise. Only one of these 5 components is actually face-centered cubic at room temperature, as this crystal structure at room temperature, nickel. And if you add them up, if you mix them in binary or ternary systems, they don't mix. If you set the composition right, but they don't always form. It's only when you're in the middle of the phase diagram, in the middle of the composition range, that they form this single structure. So this was a completely novel observation. And just to make the point, it really is completely random. These are atom probe measurements of the chromium, manganese, iron, cobalt, and nickel in a block. So each of these points here is an atom that's been pulled off the material, and you can see how they're distributed through. I mean, you can't see the crystal structure, but otherwise you're looking at atomic level, and you can see they're distributed, as far as we can tell, completely at random in this material, and that was a complete surprise. Now, I think, so for complicated reasons, to do with the fact that everyone thought this was a bit of a crazy idea, and because Alan Vincent was only an undergraduate student and therefore wasn't a very yet trained scientist to do good experiments, we weren't able to publish the results. So although he did the work in about 1980, well, it was 1980, we didn't publish it until 2004. We had to redo the work several times. It took 25 years before it was published. Partly because I went off and was doing other things. So, but I don't want to go into the story. It's an interesting story, but I don't want to bore you with it. But for complicated reasons, we didn't publish. We couldn't get the work into a shape that it was publishable. Nobody would have published it, even though we knew what the results were. And finally, in 2004, we published our paper on this. And it's just around about the same time I went off and stopped working as a research scientist, and I went off to start running universities. I took my first job as a Vice Chancellor of University of York in 2002. And I was very happy to have got this finally out the door and a publication. I was very pleased about it. We'd done a few other things, but I don't need to go into that. So I was happily or unhappily coping with people's pensions and auditing the university's books and all that kind of stuff, which is what you have to do when you're a Vice Chancellor, and occasionally being able to go to the English Literature Department and hearing all the wonderful things they were discovering about English literature and Shakespeare, or whoever, or James Joyce, and doing what Vice Chancellors do. And people began to ring me up and say, what is this amazing material that you've discovered, Brian? So to put it crudely, when we published the paper in 2004, it totally bombed. In 3 years, there were only 8 citations to that paper, the first 3 years. And I think probably they were all by me. I haven't checked, but I must have cited it a few times. There are now, we're running at about 2,000 citations a year, which is a lot. The total, we've hit 8 or it's approaching 10,000. It's about 8,000 citations. Still going up dramatically. But it took a while before it got noticed. I'd gone off to do these other things, and people began to ring me and say, what are these amazing materials you've discovered, Brian? Let me just say a few more words about it. Well, this is what they discovered. So this is what's called an Ashby map. Mike Ashby, who worked in the engineering department here and for many, many years, developed the idea of demonstrating material properties by plotting them on various so-called Ashby maps. This is one for mechanical properties where you plot the fracture toughness. So the toughness or the shapeability or the softness, the ability not to crack and fail, which is the toughness, as well as the shapeability, the formability, we can say is on this axis, and then the strength is on this axis. And the best combination of these high-entropy Cantor alloys. So this is showing it against a wide variety of different materials. If you focus in a bit more closely onto steels, which is perhaps a more sensible comparison, then these are the Cantor alloys and these are the different best quality steels. So that's what people have discovered. And I'll say very quickly a word about why that is in a minute. But let me just go on to make a few more observations, because multicomponent alloys turns out to be an amazingly complicated and rich and interesting range of materials. So this is, and it's not a small range of materials. I've already used the word gazillions, and you'll see what I mean, how gazillion-y you'll see in a minute. But just the FCC single-phase Cantor alloys, there are literally hundreds. I'm sure there are millions. I haven't counted them. There's millions of Cantor alloys. That's to say, single phase, single structure, FCC, compositions, different compositions with a random distribution on that face-centered cubic structure. The first book on the topic was by Murty, Ye and Ranganathan in 2014, and they had listed 3 pages. They updated the book in 2019, and there were 3 times as many. There's almost certainly 3 times as many again by now, so there's 10 times more than that have been studied by somebody or other. So there are millions more. There are still loads and loads of the single phase FCC cantor that haven't yet been made. And it's not just face-centered cubic. This doesn't just happen with face-centered cubic. It took a while before people began to extend the idea. Most of the single phase face-centered cubic ones are formed from elements at the back end of the transition series. There's a lot of them. There's about 10 or 12 or 13 or 14 elements there, and some main group elements. But if you take the early transition metals, you get body-centered cubic. And you get the same sort of thing. You get a very beautiful structure. These structures, I didn't mention it before. I did show you a picture of it. That's an ordinary microstructure from an optical microscope. They just look like this is what any material looks like. They don't look any different to any other material. And the same thing happens with body-centered cubic. You can mix up lots and lots of components, lots of starting elements into a body-centered cubic structure. Then that was discovered towards the end of the 2000s. Then it was discovered that you can do the same thing with compounds. You can take an aluminide. The first ones that were discovered were intermetallic compounds, like this. So cobalt aluminide or iron aluminide are known compounds with a certain structure. It turns out you can mix up loads and loads of metals on the metal sites in the crystal. So the crystal structure has a metal site, iron, and an aluminium site, and they're different. So there's 2 sort of the structures I'll show you. I don't want to get into the details of it. But you can mix up loads and loads of metals randomly on those metal sites to make a multi-component aluminide. Then, in the mid to late 2010s, they discovered you can do it with inorganic materials. So the first one was Rost et al. in Nature, demonstrated you can make this material. They made this material, a 5-component metal oxide with a single, simple, and it's perfectly random, but demonstrated to be so. And you can go up to things like perovskites, and so that which are more complicated. They're an AbO3 structure. And the A, you can mix up things on the A site, you can mix up things on the B site. And it turns out that what happens is, when you go from having single components, when you start to mix them up as alloys in mixtures of 2 and 3, they form compounds. But when you go to 3, 4, 5, 6, 7, 8, 9, 10 components, they don't form any new compounds. They prefer to mix up on the existing kind of compounds that we already know about. So we haven't discovered any special new compounds when you start adding all these different components. What you discover is the same old compounds, but with this sort of randomized multi-atom structure. So I like to think of multi-component phase. Well, let me wait till I get there. So I'm now going to turn to 3 questions, scientific questions, which I shall about these sort of materials. The first thing is, why? Why did they do this when everyone thought they? And why is it that everyone thought they didn't? It didn't go like this. The second question is, well, there's a lot of these materials. How many of them are there? And then the third one will be, why have they got such complicated properties and interesting properties? So I'll flip through all this pretty quickly. So sorry to give you a real equation, a well-known equation, but the structure of a material depends upon its free energy. And if you make an alloy, when you mix things, it's the mixing, the change between the energy of the stuff before you mix it and the energy after you've mixed it. And that's this number here. And it's got 2 bits, an enthalpy term, or an energy term, you can think of it as the same thing, and an entropy term. You know, one of the glories of 19th century science, sitting alongside evolution and electromagnetism, is thermodynamics. And thermodynamics is that when the Industrial Revolution happened, Everyone thought Newton had sorted it all out, and others. It all depended on forces and energy. And it didn't work. When they started making the machines, they didn't work right. They weren't they weren't as good as they should have been. And why? It's because they hadn't understood entropy. Now, we can understand that because most undergraduates learn about entropy in their first year, and none of us understand it. There's a famous saying, I can't remember the scientist who said it, but which is nobody ever understands that thermodynamics, you just get used to using it. But I actually don't think that's right. I think thermodynamics is dead easy. There are 2 bits in thermodynamics. There are only 2 things you need to know. And we hadn't worked out the second one. Newton had worked out the first one. The first one is that things try and reduce their energy. If I knock this on the floor, it falls off the table, it falls on the floor. That's basically Newton's law of motion, right? It reduces its energy. It goes to a lower position because the energy is lower when it's because of gravity. What people hadn't recognized was, and all the forces come in that, so every single force of nature is wound up in this term here. What people hadn't worked out was, there's another, I can't call it force, but there's another driver in the world, which is entropy, which is things don't only like to get to low energy, they like to get mixed up. Entropy is disorder. Things get disordered. And if I knock a pack of cards on the floor, I haven't got one, they get mixed up. They don't end up as a pack of cards, they end up as a mess. And that's true of pretty much anything you knock on the floor, if it's got the capability to get more of a mess. So there's a second driver. This is what wonderful scientists like Gibbs and Boltzmann finally kind of sort of sorted out towards the end of the 19th century, after others had played and understood it a bit as they went along. So when you mix an alloy, and there are 2 things which contribute to the structure. The structure is determined by this number, and there are 2 drivers. There's the change in energy, and the change in energy is what forms compounds. There's the chemical reaction between the electrons and the protons and all that kind of stuff, which we don't need to worry about in detail. But, they all interact to try and form compounds. We know that. That's what, we learn that very early in school. We like mixing things and they go bang, because they're reacting to form compounds. But there's another term, which is the entropy term, which is that things also like to get mixed up. Now, we can understand what happens. When you take copper and you mix it with a little bit of tin, everything is dominated by this. The same when you mix a bit of carbon into iron, everything's dominated by this. So beyond a very small amount, you start to get compounds, which is good at first because it helps you to tweak up the properties by adding little bits of stuff into the material. But if you add too much, forget it, because you start to get loads of compounds and it's a mess. And it's a material and it breaks up and you can't make it into anything useful. But this term hasn't yet come into play because you're not adding enough. Once you get beyond about 5 or 6 components, this term starts to become significant and worth worrying about. That's why you start to develop these random structures, because suddenly the entropy term gets big enough. Not always. If the compound forming tendency is big enough, you still get compounds, like in our 20-component material. But in many cases, you get this randomizing effect on these crystal structures because of that entropy term. So that's the answer to my first question. Second question, how many materials are there? Well, think about it. It depends on how many components we're going to mix up, and it depends how far apart the 2 have to be in composition before they're a different material. The number of components is big C, and what we call the specification is X%. That's how far you can go in composition before you can say I've got a different material. Specification is normally used sort of commercially so that you can sue someone if the material fails. When someone supplies you with a material, they supply within a specification, within a range of composition. And it's to do with how good we are at making the material and how good we are at having reasonably consistent properties. And typically for engineering, that's called the specification. If the specification is X%, if we say that, if we change the material's content by X% of one of the components, then there's N is 100 over X different composition values. That's the number of points along one of those axes in those triangles and tetrahedra I was showing you. Well, if you've got C components and different materials have got to be separated by X%, it turns out the number of materials you can have, number of points in that triangle, or you know, in the number of different composition points you can have, is this number here. It's a bit of combinatorial maths. I'm not going to go through it. You can believe me. There's a, you know, it's sort of standard stuff. Well, how big is C and X? Well, I very conservatively see is 60. There's 128 different elements now known. There's a lot of the more recent ones only last for a few nanoseconds and are toxic anyway and radioactive. Take all those out and you get down actually to about 80. But if you're really restrictive, you can get it down to about 60. But that's leaving out things like I don't know, sodium and sulfur, which is, you know, pretty useful materials actually, quite often used. But nevertheless, let's say C is 60. The reason, you'll see why I've chosen it in a second. Engineering materials are usually specified to 0.1% or 0.01%, very good materials. Sometimes a lot of chemical materials are only specified to 1%. But let's take X as 0.1%. That's not quite that conservative, but it's not unconservative. If C is 60 and X is 0.1%, the number of materials you can have is 10 to the 100, which is a googol. Which is why Google is called Google, but they spelt it wrong, I think, intentionally, I think. Now, that wasn't quite conservative. The reason I like these numbers because I like the number 10 to the 100. But but that is extremely conservative. And if you put X is 1%, you get 10 to the 40, which is still a socking big number. That's the point. So if you want to say how many gazillions am I talking about, this is how many gazillions I'm talking about. The number of atoms in the galaxy is fairly well known to be about 10 to the 66 atoms. We don't really know how many there are in the universe. It's been hypothesized it's 10 to the 80. We're not quite sure how big the universe actually is. So what I'm telling you is the number of materials is on the order of the number of atoms there are in the universe, or at least in the galaxy. A lot, an awful lot. And the number we know is incredibly small. If you look at the numbers we've looked at in these little, you know, regions, so there's really millions and millions and millions and trillions that we've never even made, even though there's been now a decade and a half, or nearly, it's about a decade and a half of reasonably intensive, about a decade of intensive study of these multicomponent materials. Now, why do they have unusual properties? And this is another, I hope you'll find, interesting feature of these materials, which I show by a schematic. It's not a real structure anymore. This is a 10-component system on a square lattice, and the components are A to J, and the square lattice is a two-dimensional, so it's not real, obviously. The most obvious point, which you can see here, is that if every atom's the same, or if you have a crystal of copper, every atom's copper, and if you have a crystal of silicon oxide, every atom, every lattice point has a silicon oxide molecule. Then the properties at each lattice point, at each point in the crystal, are the same, fairly obviously, because it's the same atom or same molecule. And fairly obviously, in these materials, it's not the same, because we've got different atoms. And it's obvious that there's at least, in a 10-component system, at least 10 different properties, right? Because you've got 10 different atoms. But there's a lot more, because the properties of this I atom here doesn't only depend on the fact it's an I atom, it depends upon the fact it's interacting with the atoms adjacent to it, this group of near neighbours, we call them. And if you take a different I atom, which I can't now find one, here's another one, the near neighbours are different. Okay? So the number of local properties is varying in these materials as you go from point to point, very largely. It's not just 10 different properties, there's a lot bigger number. I'll show you how many in a second. Well, I'm going to show you immediately. But no, I want to say something first. The second most obvious thing is, because the atoms all have different size and different electronic structure, the structure's full of strain. Because, you know, this H atom's big and this B atom's a lot smaller. So the crystal is sort of stretched and strained everywhere. because of that difference in the properties locally. So the most obvious property which is different is the strain, the mechanical and the electronic strain in the material. And we can look at how big these effects are. So I've done the calculations. It's another combinatorial mass problem. But if you have the original Cantor alloy with 5 different components, and you include the second near neighbours, the question becomes how many ways. There's 12 near neighbours in face center cubic, and there's 6 second near neighbours. So there's 18 atoms which affect a single atom at the center. That's 19 atoms. The question is, how many ways can you distribute 10 different kinds of atom, or 5, on 19 different sites? And it turns out, if you have 5 components, it turns out to be this number, which is just about 20 trillion. So there's 20 trillion different local structures. That's big enough that you need a piece of material a few microns in size to contain it all. If you have a 10-component system, you need a piece about this big to contain it all. So it's actually more. These materials are more like macromolecules in the biological macromolecules, because to contain all the different structures they have that they can take, you need a really big chunk of material to do so. And is it true that they have a lot of strain? Well, if we take the 5 components here in the Cantor alloy, forget these 2, the size difference is about 2.5%, which is about 3 picometers. And 2.5% you would expect, therefore, is a big strain. That's what it would be if they didn't change their size when you mix them. But we've also got measurements of what it is, and it turns out that's about right. Neutron diffraction says about 2 picometers. Synchrotron X-ray says about 5 picometers, about 2% and about 5%. In the body center cubic materials, it's a little bit higher. It goes up to 7%. These are big strains in the material. So there's this landscape of varying strains going over enormous distances in these materials, and that's what gives lots of the interesting properties. So to go through them very quickly, there's 20 trillion different structures around what's called a vacancy. If the way atoms move around in solids, crystals, is by jumping into vacancies. There's vacant, occasionally an atom missing. And the structures vary enormously for the same reason, around the vacancy. So if you don't have a multi-component material, if you have a single component material, every time an atom jumps, it's got the same profile in energy. It jumps from its starting position to a new position and goes over a saddle point. So all the jumps it does are the same. But if you've got in one of these multi-component materials, the jumps are all different. And what happens is it slows down the overall rate at which atom motion happens, because they get stuck in low energy positions and they start going round and round in circles and things like that. That's very, very important. Because of these local strains, they get stuck, and that means that they're very resistant to degradation. They're very good at radiation resistance. They don't degrade under radiation anywhere near as much as other materials. They're very good at high temperatures. They don't degrade so easily when exposed to high temperatures. They're very good against corrosion. So they're resistant to all these things, mainly because of these local structures. Going on to what about the mechanical properties we talked about? Well, the mechanical properties depend upon not vacancies, which is a point defect in a crystal, something called dislocations, which I'm not going to try and explain in any way, but this is a dislocation in a face-centered cubic multi-component material, and the dislocations are lines of a defect in the crystal structure, and the reason face-centered cubic metals are so soft is because they move, and that causes the planes to roll over each other very easily. You don't need to know the details of it, but these dislocations don't move so easily. I'm running out of, oh no, there it is. You can see they're sort of very wiggly, and that's because of those local strains. So you do get the shapeability, you do get the fracture resistance, but it all happens at a much higher strength, which is why they've got such good properties. And the theory and experiment of this is quite complicated. I'm not going to go into the details, but it gives quite good results. Finally, The same thing happens with local surfaces inside the material. Most materials have several crystals inside them, and they have surfaces, and it turns out they've got great catalytic behavior because there are 20 trillion different structures on the surface. So you get much higher catalytic efficiency because you've got a wide range of different energy sites at which catalysis can happen on the surface. I won't bother with that. So to summarize, the Cantor alloy itself, the range of Cantor alloys, the face-centered cubic ones, have the best low-temperature cryogenic properties, strength properties of any known material. Some of the BCC ones are called Senkov alloys now, after Ivan Senkov, have some of the best high-temperature strength properties known. There's tremendously good corrosion, radiation, damage resistance. If you take these compounds, which have only much more recently begun to be studied, they're tunable properties, which are tunable by composition, which has never been capable before. We've always used pure single crystals of things. So piezoelectric materials, or solar energy converting materials, or battery materials, we can tune them by tuning the composition, and that's really a great freedom. And finally, these materials are important for recycling and reuse, because as we recycle things, which we must do, we start to mix the elements up more, and we start to make more multi-component materials. So, human history is the history of new materials. All materials are alloys. There's gazillions of them, and there are wonderful new materials to be found. And generic alloys are needed for recycling. Thank you very much.